Welcome to the Explainer. You know, our whole world, everything, from the smartphone in your pocket to the food on your table, it's all built on energy. But have you ever really stopped to think about what energy even is? Not just where we get it, but what's actually happening on a deep, fundamental level when we start a car or just flip on a light switch? Well, today we're going to peel back those layers and look at the engine that runs our world.
So you look at a steam engine chugging along, and then you look up at a star that's been burning for billions of years. They seem worlds apart, right? But what if I told you the source of their power is fundamentally the same? The answer, it turns out, is hiding in plain sight, in the invisible connections that hold everything together.
You know, for most of human history, our world moved at the speed of muscle. That was it. Then, bam! The 1800s hit, and the Industrial Revolution gives us steam power from burning coal. A little while later, the internal combustion engine shows up, and suddenly we have gasoline. Fast forward to today, and there are over 500 million cars on the road. Each step was a massive leap in unlocking more and more energy, and it's made our world incredibly hungry for fuel.
All right, so to really get what fuel is, we first have to talk about energy itself. And it turns out that all energy, doesn't matter where it's from, basically comes in two flavors. You can think of them as two sides of the same coin. There's the energy of what could happen and the energy of what is happening right now.
First up is potential energy. This is basically stored up energy. The best way to picture it is to think of a massive dam holding back a lake. That water isn't moving, but just by being held up high like that, it's packed with an incredible amount of potential to do something. It's just waiting.
And when that waiting is over, that's when you get kinetic energy. This is the energy of pure motion. So you open the gates of that dam, and all that stored potential energy converts into the kinetic energy of that rushing, powerful water. And that's the energy that spins turbines to make electricity. One just turns into the other.
So let's lock this in. Potential energy is the possibility, the stored up what if. Kinetic energy is the action, the here we go. And this switch, this transformation from stored to in motion, is the secret behind almost every single power source we use.
Okay, so how does this connect back to fuel, like a log for a fire or gasoline? Well, the energy isn't really in the liquid or in the wood itself. It's stored in the chemical bonds, the tiny connections holding all their molecules together. This is a form of potential energy, just like the water behind the dam. And when you burn that fuel, you guessed it, that's like opening the floodgates.
So how exactly do we open those chemical floodgates? It all happens through chemical reactions. And these reactions are all about giving and taking energy. To keep track of it all, we need to draw a little circle around what we're looking at. In chemistry, scientists talk about a system. The system is just the specific chemicals that are reacting and what they turn into. Everything else, the air, the beaker, you standing there watching, that's all called the surroundings. So for a barbecue, the system is the propane and oxygen reacting. The grill, the air, the hamburger, that's all the surroundings.
Now that barbecue is what we call an open system. It's releasing both energy, heat, and matter, the smoke and gases, out into the surroundings. But then, think about a glow stick. You crack it and it gives off energy as light. But all the chemicals, all the matter, stays sealed up inside that plastic tube. That's a closed system. This difference is really important for figuring out where the energy goes.
And this all leads us to one of the most fundamental bedrock laws in all of science. You can't just make energy out of thin air, and you can't make it disappear. It can only be converted from one form to another. So, if our little chemical system loses energy, the surroundings have to gain that exact same amount. It's a perfect balance.
This simple law gives us two major types of reactions. If a reaction releases energy, we call it exothermic. Think exo for exit. The energy exits the system. The things it creates have less potential energy, and that extra energy heats up the surroundings. The opposite is endothermic. Think endo for into. The reaction actually has to pull energy in from the surroundings, making them feel colder.
Let's look at a classic exothermic reaction, burning methane, which is pretty much what natural gas is. When methane and oxygen react, they rearrange themselves into new molecules, carbon dioxide and water. But here's the key. These new molecules are more stable. they have less potential energy stored in their bonds. So where did that leftover energy go? It got kicked out as the heat and light of a flame. Energy is literally a product of the reaction.
So we have literally built our entire modern world on these energy-releasing chemical reactions. But what if I told you that all the energy from burning fuel is just a tiny, almost insignificant spark compared to the power that's locked deep down inside the atom itself?
Yeah, that's right. As powerful as a rocket launch or a huge explosion seems, that's just chemistry. The true powerhouse of the universe, well, it operates on a completely different level.
This is nuclear fission. Here, we're not just rearranging the chemical bonds on the outside of atoms. Nope. We are splitting the very core of an atom, its nucleus. And when you split a heavy nucleus, like uranium, it releases millions of times more energy than any chemical reaction. This is the power behind nuclear reactors. But believe it or not, there's a process that's even more powerful. Nuclear fusion. Instead of splitting big atoms apart, fusion is all about smashing tiny atoms, like hydrogen, together to make heavier ones. This is literally what powers the sun and every other star. It's the ultimate cosmic furnace.
So, how much more energy are we really talking about here? Well, if you take a specific, small amount of hydrogen and fuse it together, it unleashes 1.7 billion kilojoules of energy. That number is so huge it's almost hard to get your head around. It's a total game changer in the scale of power we're dealing with.
All right, so let's put all of this into perspective. Because when you see these different types of energy release lined up side by side, the difference in scale is just, well, it's mind-bending.
Take a look at this chart. On the far left, that tiny little sliver of a bar is the energy released when steam turns into water. Next to it, a powerful chemical reaction, making water from hydrogen and oxygen, gives off a few hundred kilojoules. And then there's nuclear fusion. At 1.7 billion, its bar isn't just bigger, it completely dwarfs the others. They barely even register.
In fact, our source material puts it this way, and I love this visual. To actually draw that nuclear energy bar on the same scale as the other two, you'd need a piece of paper about 1,000 kilometers long. That's the distance from Paris to Berlin. That is the absolutely staggering amount of power we're talking about, locked inside the atom.
And this brings us right back to where we started. The history of our civilization is a story of climbing an energy ladder, from muscle to steam to gasoline. We've pretty much mastered chemical energy, but the next rung up on that ladder, the power of the atom, offers this almost unimaginable leap forward. The science is there, so the final question really isn't about physics or chemistry anymore, it's about us. Can we learn to safely wield that kind of power?